Reverse reactions. Some reactions can proceed in both forward and reverse directions, and even sometimes both at the same time. When the rates of the forward and reverse reactions are equal and the concentrations of the reactants and products don't change, the system is at equilibrium. Reaction favoring. Forward reaction favoring is what happens if the rate of the forward reaction is greater than the rate of the reverse reaction, and there is a net conversion of reactants to products. If it's reverse reaction favoring, the rate of the forward reaction is less than the rate of the reverse reaction, and there is a net conversion of products to reactants, as shown in these pictures. After time, equilibrium is reached. Over time, the rates will slow down and the products and reactants will not become equal, but they will stay constant. When the system reaches equilibrium, neither direction of the reaction is favored, and the rates of both forward and reverse reactions are the same. The products and reactants, however, do not have to be equal in concentration at equilibrium, only the rates. So there's three types of equilibrium. Equilibrium can vary in three different ways in response to the K value. So when K is equal to 1, and with this graph, the reactants and products essentially come very close. And this means that the concentrations of reactants and products are almost equal or equal at equilibrium. And where K is greater than 1, the product spikes over the reactants and the reactants goes below the products, and at equilibrium, the graph should look like that. And this essentially means that the reverse rate constant is lesser than the forward rate constant. When K is less than 1, the graph should look about like this, where they don't cross. And this essentially means that the reverse rate constant is larger than the forward rate constant. All right, here's an AP style multiple choice question. It says a reversible reaction is represented by the equation above, right here. And the amount of reactants and products at time 1 and time 2 are shown. Based on the diagram, what can we infer about the rates of the forward and reverse reactions over time? So we have A, B, C, and D. A says, over time, the forward reaction is favored because the concentration of AB increases. B says, over time, the reverse reaction is favored because the concentration of A decreases. Letter C says, over time, the system reaches equilibrium because the total number of A and B atoms do not change. And letter D says, over time, the system reaches equilibrium because the reaction stops. The answer is B. Over time, the reaction rate is favored because the concentration of A decreases. And this is shown in the diagram here with the times, because if you look at how many A to B, the A and B to AB, like the ratio, it changes and the concentration of A decreases, showing that the reverse reaction is favored. So some key takeaways for 7.2 is when the rate of the forward reaction is greater than the rate of the reverse reaction, there's a net conversion of reactants to products. This does not mean it is at equilibrium, and this is vice versa with when the rate of the reverse reaction is greater than the rate of the forward reaction, there's a net conversion of products into reactants. And this is also not at equilibrium. Those two are essentially vice versa. We also have, in this case, we would see the concentrations of the products increase and the concentration of reactants decrease. And this is just an overarching theme. Over time, if the rates of the forward and reverse reactions became equal, the reaction is said to have reached equilibrium. That is all I have for 7.2. Thank you for listening.